interior point methods. So let me start by quickly reviewing what we did last time. So last time we spoke about primal dual interior point methods for linear programming. So remember, we have looked at the two problems, the primal problem in standard form, it's the one on the left, and then the corresponding dual problem that in the case of linear programming, it has that nice feature that is also a linear program. Okay? And then there was a certain notation that we introduced to define the algorithms. The first piece of notation is that F0 set that represents the set of strictly feasible solutions for both the primal and dual problems. And one thing that I want to reiterate, that this is really a neat property of, a neat way of thinking about F0. So if you think about your, say, primal problem, the primal problem looks perhaps something like this, right? This would be the set of points that are feasible for the primal problem. And then the dual problem, right? The dual problem would look like another linear programming problem. So this, think about this as ys such that A transpose y plus S is equal to C, S greater than or equal to 0. And then in the primal problem, we want to minimize C transpose X. In the dual problem, we want to maximize B transpose Y. And the two, we have that property of strong duality, the two optimal values match. Now, if you think about F0, so F0 is like if we looked at all the interior points here and the interior points here. And then there is this neat connection between F0 and Rn++. So we can think about these pictures here, but if you think about the points that you have here, and you look at this map, to use the notation from last time, this is a bijection. So this is really neat because we can visualize, let's say, everything that happens in the in our primal and dual feasible regions. We can kind of develop some intuition, some geometric intuition for that by thinking in terms of this correspondence. All right, so that was F0. Then we had that for X and S positive, mu is essentially some measure of the duality gap. So mu of XS is the dot product of X and S divided by N. So if you have a primal feasible and a dual feasible points, the difference in the objective functions is X transpose S. Mu gives you an idea of how far you are from optimality, the duality gap. Finally, the neighborhood, the two neighborhood is defined like that. So recall also something else that I'm going to use a little bit later. So recall the central path equations. So the central path equations are these equations, A transpose Y plus S equal to C, AX equal to B, and XS1 equal to tau 1. And of course, X and S positive. So the central path are the points that satisfy these equations. And again, you can think about that geometrically as a couple of curves here. This would be the primal part of the central path. This would be the dual part of the central path. Or if you think in terms of this correspondence, the central path, if you think in, say, Rn++ via this correspondence, the central path here is this ray where all of the components are a multiple of 1. Okay. Now, the key step of the algorithm, and this is something that I realized from questions that I got after last time, maybe this is something that we want to look at again, because what we are discussing today is taking a step further. The key step in the algorithm, the key step in the algorithm is to update our iterates. So throughout the algorithm, we are going to have points that are here, and then we are updating the points, ideally getting close to the optimal solution. And likewise in the dual. So we have points that are, and we are generating both primal and dual points. Or if you think in terms of this correspondence again, what we are doing is generating points, if we were to visualize them here, generating points that are converging to the optimal solution. So the heart of the algorithm is what is called the Newton step, is that update from the current iterate to the next iterate. So what is the Newton step? The Newton step is we attempt to chase points that satisfy these equations. We want to chase points that are on the central path, very much as you do for the barrier method. The difference is that this is a primal dual method because we are doing that both for the primal and the dual problems. And for the primal and dual problems, the equations are here. So the Newton step to chase points that satisfy these equations is obtained as follows. We take the equations here, so that is these three guys, and we linearize those equations. So linearizing those equations gives us these equations that are what define the Newton step. Okay? So maybe one thing that I'm going to do twice today, but I think this is important. So this is kind of a little detour. So Newton's method, you can think about Newton's method in two possible ways. Okay? So if you're thinking about optimization, you want to minimize, let's say, f of x, right? So you go from a current point to a new point where the new point, the update here, okay, this update is the solution to this system of equations, delta Hessian of f of x, delta x equal to negative gradient of f of x. Okay, so this is Newton's method for optimization. And Newton's method for solving equations is, suppose that we want to solve a system of equations that is g of x equal to 0, a nonlinear system of equations, kind of like this system of equations. So what we do here is from x, we produce a new point, x plus delta x, where the delta x here is the solution to the following. We take the derivative of g of x, delta x, equal to negative g of x. Okay? So both of these can be seen as the same thing. If you think about g of x as being the first order conditions, g of x as the gradient of f equal to 0, observe that both of these things are doing exactly the same thing. The Hessian is nothing else than the derivative, the Jacobian of the gradient of f. Okay, so these two things are essentially identical if you think in terms of optimization, unconstrained optimization as the same thing as solving the optimality conditions. Okay, so back to our problem here. The Newton step is what you get when you linearize. You think about this left-hand side here as your g. So you want g minus the right-hand side equal to 0. So that's what leads to this system of equations. Now, why are the first two 0 here? So if we start with feasible points, the first two equations are already satisfied. So these two, there's not going to be any update there. Those are 0. And then this was the main algorithm that we discussed last time. It's quite a simple algorithm. You pick some constants. The two constants define two things. They define how close you're going to be to your central path. So the two neighborhood defines some set of points that are near the central path here, or if you think in terms of the original space, the two neighborhood defines some neighborhood of the central path here. So we start with a point that is in the two neighborhood. And we have these two parameters to play with, delta and theta. Theta declares how close we are going to stay to the neighborhood. And delta has to do with how we are decreasing the value of tau. And the update is done by performing one step of Newton's method. So from iterate k to get to my new iterate k plus 1, what I do is solve the system of equations here that defines the Newton step at the current iterate, so xk, yk, sk, and then we update to the new one. And then the key theorem is that this algorithm generates points that are near the central path. They are in that small neighborhood. And mu goes to 0 linearly. Now, since mu goes to 0 linearly, that means that the duality gap between primal and dual also goes to 0 linearly. And that means that, roughly speaking, we can expect convergence, the duality gap to be, if we wanted to get to epsilon, roughly speaking, we will need to perform about log of 1 over epsilon steps. Okay? So that was the main thing we did last time. Then there was also this business of a long step method that has a similar kind of behavior. And then the very last thing is that we did last time was an infeasible interior point method. So infeasible means that we do not necessarily satisfy the first two conditions here. The only thing that we satisfy is the last one. So an infeasible interior point method, somehow we need to think more broadly in terms of the central path. The Newton step equations now are like this. We have terms in the first two equations because the current iterate may be infeasible. And then you have, again, a very similar template. The key step at each iteration, once again, is to solve the Newton step. So we solve the Newton step, and then an important difference is that now that we are infeasible, we may have to perform some kind of line search to get an acceptable point. So we don't take a full Newton step, as in the short step method, but we take something that does some line search. So it takes a step length alpha, and then we do that. Okay. So those were I guess the key points that we went over last time. Let me pause here for a moment in case there is a question, anything about what we did last time. All right. So one thing that I want to reiterate, if you think about, this is something I mentioned last time. This is a very clean algorithm with a very clean theorem, but it's one of those things that is very clean and very nice theoretically. In practice, you would not really implement this algorithm. If you did, it would be a slow algorithm. In practice, you really implement something that looks more like this uglier algorithm. Okay? Now, in practice, you would do something that is even a little more hacked version of this. You wouldn't even worry about the neighborhoods. You would just ensure that the step length, you would take a very aggressive step length, almost 1, ensuring that your x and s remain positive. So there is an interesting kind of paradox in interior point methods. Sometimes some optimizers call this the gap between theory and practice. The gap is that there are certain elegant algorithms that have nice theorems, and then there are implementations that use the ideas of the algorithms, but they really push things well beyond what the theorems prove. And the latter tends to work very well and solve problems very efficiently. So that's kind of an interesting sort of issue about interior point methods. All right, so what we are going to do today, one more thing about interior point methods that I would like to highlight. If you look at either the infeasible version or the feasible version, the short step version, the bulk of the work, the bulk of the computational work is in computing the Newton step. computing the Newton step involves solving a system of equations. Okay, so computing the Newton step is a relatively expensive step. Everything else in the algorithm is easy. The Newton step is kind of the bottleneck. Okay? And there is all sorts of additional matters that have to do with how we can solve the Newton step efficiently that have to do more with numerical linear algebra than with optimization. But this is an important distinction between Newton's method. Integral methods essentially are based on Newton's method and, say, gradient methods. Gradient methods, each iteration is a lot cheaper than a Newton method. The trade-off is that Newton's method converges very fast, linearly for linear programming, whereas gradient methods may have a slower rate of convergence. All right, so with that, let me tell you what we are doing today. What we are doing today is taking a very nice step from linear programming to semi-definite programming. And I want to draw a little diagram that I drew a few weeks ago when I first spoke to you. If you think about the class of convex optimization problems, this is a large class of problems. Linear programming is a small class here. It's very important, it's very powerful, it's very popular, but it's a small subclass of optimization problems, of convex optimization problems. Now, semi-definite programming is a much, much larger class of problems. So semi-definite programming, if you were to put it in, say, this diagram, would be something a lot bigger that includes linear programming, but a lot more. So what I would like to show you today is how a lot of the machinery that we already discussed for linear programming, this primal dual machinery, has a nice extension to semi-definite programming. Okay? So that's the main message today. And then at the end, I want to show you how you can actually solve some small semi-definite programs with these two solvers that are freely available, Sedumi and SDPT3. So that's the plan for today. So what is semi-definite programming? Okay. What is semi-definite programming? So semi-definite programming is that type of problem where it looks a lot like linear programming. So if you compare that with the problem that we discussed last time, it looks almost identical. Okay, so we have a linear function. We have some linear constraints. The difference is that instead of x greater than or equal to 0, we have something that is like a generalized inequality. So x positive semi-definite. So here, the variable x of the optimization problem is a symmetric matrix. And the last constraint there, x greater than or equal to 0, is that symmetric matrix should be positive semi-definite. Okay? Other than that, it's extremely similar to linear programming. I've heard comments from some optimizers that say, semi-definite programming is like linear programming of the 21st century. Right? Linear programming was last 20th century. Semi-definite programming is 21st century linear programming. So what did we do with linear programming last time? We discussed the dual. So in semi-definite programming, there is also a very similar duality property. So we have an associated dual problem. The dual problem, so I guess let me put here again the primal SDP. The primal SDP is this, Cx subject to Ax equal to B, x positive semi-definite. So that's the primal. Then the dual is a very similar kind of template as with linear programming. What defines my constraints in the primal now defines the objective in the dual. And what defined the objective in the primal now defines the constraints in the dual. And then this A is a map that goes from Sn to Rm. It's a linear map. So we need something that would be kind of like the transpose of A. So that's what is called the adjoint of A. So A star goes from Rm to Sn. Okay. So that's the adjoint. Maybe I could be more explicit here. So typically, A of x is defined in terms of a bunch of matrices, A1x up to AMX. So if this happens, then A star of y, the adjoint is the sum of yi, ai. Okay. So observe that is if you were to take the matrices and just convert them into columns, A star and A are kind of transpose of each other. Okay? So I guess I equal 1 to m. So that's the semi-definite programming dual. Now, let's try to go back to what we did on Monday. Okay? We spoke about the primal LP problem and the dual LP. And then the very next thing that we did was discuss some neat duality relationship between these two problems. So that's exactly what we are going to do now. So we have weak duality. We have weak duality just as we did for linear programming. So what does this mean? Again, the primal problem attempts to minimize a linear objective. The dual problem attempts to maximize. And then there is this neat relationship that for any primal feasible problem and any dual feasible problem, the dual objective is a bound on the primal objective, a lower bound on the primal objective. Okay, so we have weak duality. Now, again, if you were to write the proof of this is almost identical to the proof of weak duality for linear programming. We take the difference Cx minus By, and if you just plug through the equations, you get that the difference is X transpose S, and that has to be greater than or equal to 0 if both X and S are positive semi-definite. So weak duality is a one-line proof. And then we have this business of strong duality. Okay, so for strong duality, this is interesting because this is a key distinction between linear and semi-definite programming. In linear programming, we essentially always have strong duality. We always have strong duality, except in some pathological cases when maybe the primal problem is unbounded or infeasible. But if the primal problem is feasible and bounded, then we have this very nice duality in linear programming. In semi-definite programming, there is a subtle distinction, and I want to spend a little bit of time on this because it's kind of a neat way of appreciating the differences between linear and semi-definite programming. There are many similarities, but there are also some key differences. So duality is one of those. So when does strong duality hold? This is something that has come up in the class in previous times. If we assume a certain kind of regularity condition, if we assume that both the primal and dual problems are strictly feasible, so strictly feasible would mean that you have a feasible solution here where X is positive definite. Okay? And in the dual, a strictly feasible solution would be when S is positive definite. So if both problems have that regularity condition, that's called the Slater condition, if they are both strictly feasible, then both of their optimal values coincide, they're the same, and they are both attained. Okay? Now, if we do not have that condition, then duality may break down. So this is kind of like a really subtle distinction between linear and semi-definite programming. So let me give you a couple of examples to show how strong duality, that nuance, strong duality is a little more finicky in semi-definite programming than it is in linear programming. And again, the takeaway is that if we have a suitable regularity condition, namely Slater condition, then we can rest assured that strong duality holds. So I want to show you these examples because I believe that these examples are key. These are things that everyone who learns about semi-definite programming should know about these examples. So these are examples that show in a certain kind of canonical way that strong duality may not necessarily hold. Okay? So I want to discuss these three examples. They're very small, very cute examples that, again, have to do with the failure of strong duality. So let me go through the first one. The first one is, so let me see. The first one, if you look at that first example, so that's this problem 2x12 subject to 0x12, x12, x22, positive semi-definite. So this is equivalent to having mean Cx, A1x equal to B and x positive semi-definite for C equal to, well, I need to get this in the objective, right? So I need to multiply x by something and get the sum of the off-diagonal elements. So C should be 0, 1, 1, 0. Okay? And then the constraint here is that the first entry should be 0. So A1 and B should ensure that the first entry is 0. So A1 is the matrix 1, 0, 0, 0. And B is the vector, just one element, 0. So the dual will be the following problem. So again, remember, the dual is max B transpose Y, right? So the dual is going to be max. It's kind of a peculiar dual because the objective is kind of trivial, right? 0 transpose Y. But, you know, that's still a number. 0 is legitimate, so let's put it there. And then the constraints would be that A star Y plus S should be equal to C. So what that means is that the constraint is A, so that's this, times Y, so we get Y, 0, 0, 0, less than or equal in this order to C, so that's 0, 1, 1, 0. Okay? I just wrote it without the slack variables to write it a little more simply here. So if you look at the primal problem, okay? If you look at the primal problem, observe that we have the constraint is that that matrix has to be positive semi-definite. All right? That matrix has to be positive semi-definite. The 1, 1 entry of that matrix is 0. So if you think about that for a moment, okay, I need the eigenvalues of that matrix to be positive semi-definite. In particular, the determinant of that matrix has to be positive. Okay? But if you look at the determinant of this matrix, the determinant of this matrix is 0 minus x12 squared. So the determinant of that matrix can only be non-negative when x12 is 0. So here, this guy, positive semi-definite, this implies this can only happen when x12 is equal to 0. Okay? So the primal problem, so the primal optimal value is 0. Okay? Now let's look at the dual. For the dual constraints. The dual constraint is this constraint that we can rewrite as, I guess, minus y, 1, 1, 0, positive semi-definite. Okay? So is there any value of y that would make this guy positive semi-definite? And again, let's think about that matrix. For that matrix to be positive semi-definite, the eigenvalues have to be non-negative, or in particular, the determinant has to be non-negative. But if you look at the determinant of this matrix, no matter what y is, the determinant will be minus 1. Okay? So this matrix, so this can never happen, no matter what y is. All right? So the dual problem is infeasible. So see, this is the strange pathology here, right? The primal problem is perfectly fine, bounded, feasible. It has an optimal solution, 0. Whereas the dual problem, in this case, the dual problem here, is infeasible. Okay? So this is the first example. Let me maybe, I guess I'm okay with time, so let me go through the second example. So the second example is a little bit different, but I think it's still interesting because it shows a different type of subtlety that could appear in semi-definite programming. So the second example is this other example, mean x11, subject to these constraints x11, 1, 1, x22, positive semi-definite. Okay? So again, this is the same as minimize cx, subject to a1, x equal to b, x, positive semi-definite, for c equal to 1, 0, 0, 0, so that my objective is the first entry, the 1, 1 entry. And A1 here, A1, I should pick A1 so that these two guys are forced to be 1. So the way to do that is to put, to pick the off-diagonal elements, right? 1, 1. And I want the sum of these two off-diagonal elements to be equal to 2, so that they both have 1. So I want that, and B should be 2. All right? So that's A, B, and C. So then the dual will be to maximize B transpose Y, so that's maximize 2Y, right? And then the constraints are that A1Y, so that's 0, Y, Y, 0, B less than or equal in that order to C. So that's 1, 0, 0, 0. Okay? So if you think about this for a moment, again, we can reason very similar to how we reasoned before. It's easier to look at the dual first. So the dual optimal value is, so if I want this constraint to hold, if I want that constraint to hold, again, by thinking in terms of the determinant, that you realize that Y has to be 0. So the optimal value is 0, attained at 0. Okay? Attained at Y equal to 0. What about the primal problem? What about the primal problem? What is the optimal value for the primal problem? I want this matrix to be positive semi-definite, right? I have 1, 1 in the diagonal, and I'm free on how I set 1, 1 off the diagonal, and I'm free on how I set the diagonal elements. Okay? So think about that for a moment. The diagonal elements, because the matrix has to be positive semi-definite, the diagonal elements have to be big enough, positive, that the determinant is positive, right? So we should have the determinant here, x11, x22 minus 1, that should be positive. And then we can set x11 and x22 sufficiently positive so that that happens, right? So if you think about that, you realize that the primal problem the optimal value is 0, because we can pick x11 arbitrarily close to 0, and then pick x22 then arbitrarily large so that it compensates, but it is not attained. It is not attained. Okay, so again, this is a very kind of peculiar subtlety that occurs with semi-definite programming. In linear programming, whenever we have a linear program that is feasible and bounded, it automatically attains its optimal value. In semi-definite programming, that does not happen. Okay? And then in the last example, I'm going to leave that as an exercise for you. You can play the same game, but let me just tell you the punchline. In the last example, so here, in this last example, so I'll skip the details. You can work them out if you're interested. If we have this this semi-definite problem, x12, x22, x23, yeah, 1 minus x22, yeah, x23 and x33, if we want that. In this case, you actually need two matrices. You need two constraints for the primal. You want one constraint that takes care of making this guy equal to 0, and another constraint that ensures that these guys here have those proper values. But the key point here is that in this case, the dual, again, I'll skip the details, the dual turns out to be max 2y2, and then the constraints are of this form: y1, 0, y2, 0, 2y2, 0, y2, 0, 0, less than or equal to 0, 0, 0, 0, a, 0, 0, 0, 0. And in this case, the optimal value here is equal to 1 and is attained. And in this case, the optimal value is equal to 0 and is also attained. Okay, so this last example shows that also that kind of pathology could occur. You can have both primal and dual attain their optimal values and be a positive gap between them. Okay? So again, the main point of these examples is to highlight the fact that strong duality requires a little bit more. Now, there is something nice about the condition that we need for strong duality. The condition that we need for strong duality very frequently holds in many problems of interest. For example, the nuclear norm minimization that satisfies this, the theta function that I may have a chance to mention later on again. All of those satisfy the Slater condition. And interior point methods also conceptually require the same condition so that we can travel in the interior of the feasible region. So the strong duality, the conditions that are required for strong duality are not obscure conditions, are very kind of natural conditions, if you want. All right, so here is something nice that again should ring a bell. So if we know that strong duality holds, for example, you have primal and dual Slater conditions. If you have strong duality, then we have something that are like the KKT conditions, or something that looks a lot like the optimality conditions for linear programming. So what are the conditions? To solve the pair of primal and dual semi-definite problems, now we need to solve those equations. And the last constraints there, that x and s be positive semi-definite. Okay. Now, there was a student here a little before I came to Carnegie Mellon, like in the 90s, a very good student who tried to develop a simplex algorithm for semi-definite programming. And he really marketed that, but somehow it didn't really catch on. So there are attempts at developing things that are like the simplex method for semi-definite programming. But the main breakthrough, algorithmic breakthrough for semi-definite programming was really the extension of interior point methods, the kind of algorithms that we discussed last time, to this problem. And there is a neat kind of historical remark. So interior point methods were independently developed by these two Russian guys whom, if you are in optimization, you always hear about these guys. These guys are like, these gurus of optimization, Nesterov and Nemirovsky. And at the time that they developed interior point methods for semi-definite programming, they both were in the Soviet Union. This was early 80s or so. They left right around that time. Nemirovsky went to Israel, and Nesterov went to Belgium. Nemirovsky now is in Georgia Tech. And then at the same time, Farid Alizadeh was a PhD student And he also independently developed all the machinery of interior point methods for semi-definite programming, which was really a remarkable achievement for a doctoral student. It's kind of a nice bar, a nice model to emulate for those of you who are in grad school. And then the topic had this immense amount of research in the 90s. Essentially, many people got excited about semi-definite programming because it offered the opportunity to extend a lot of the machinery that we had for linear programming to a much bigger class of problems. So what I want to tell you over the next half an hour or so is kind of the gist of how this extension works. Okay. So the first key step is to observe that the optimality conditions are a lot like the optimality conditions for linear programming. And then if we want to think in terms of interior point methods, then we want to think in terms of something like the central path, a neighborhood of the central path, and some sort of primal dual method. And that's exactly what we are going to do. Okay? So if you were to do something like the barrier method for semi-definite programming, what would you do? So if you are going to do, say, barrier for the primal SDP, here we have our primal SDP, right? So then we approximate that with, we replace, this is the difficult part, the inequality constraint. So we replace this with a barrier function. Okay, we replace this with a barrier function. So the barrier function is this function. A tau log of the determinant of x. So let me say a word about this function. The function f. So this function f, I'm going to call it f, is defined from the set of positive definite matrices to R that takes x and maps it to negative log determinant of x. So observe, so this is called the logarithmic barrier function. This is the logarithmic barrier function for Sn plus, for the cone of positive semi-definite matrices. So observe the following little neat fact. F of x, that is negative of log of determinant of x. The determinant of x is the product of the eigenvalues of x. So this is negative log of the product of the eigenvalues of x. Okay? And if you think about the properties of the log, this is negative sum of the log of the eigenvalues of x. Okay? So there is this kind of really cool connection with the logarithmic barrier function in linear programming. Okay, so the log barrier function in linear programming. So that one was negative sum of log of xj. Remember that? That was what we spoke about last week. Oh, I'm sorry, last class, Monday, and what Ryan had mentioned also a couple of weeks ago. So observe that what we do is, so Rn plus is kind of extended to Sn plus, right? And then the same logarithmic barrier function kind of extends to this log barrier function for Sn plus. Okay? Now the log determinant appears, I'm sure that some of you have seen this in other places, probably places that I haven't seen it. It doesn't appear just in interior point methods, but it also comes up in some statistical models. So this is kind of a key object for positive semi-definite matrices. All right. Now, it does what we would like a barrier function to do. That is, that function penalizes, it blows up if we approach the boundary of the semi-definite cone. So if one of the eigenvalues gets too close to 0, then the corresponding log term here goes to minus infinity, and then the barrier function blows up. All right, so now what happens to these two problems? Again, as we did last time, I'm not going to repeat that, but it's a very similar reasoning. The two problems are essentially Lagrangian dual of each other. So if you think about the barrier problem for the barrier method for the dual problem would be the one that is at the bottom. So they both have this nice duality connection. And very much like we did for linear programming, the optimality conditions for both the primal and dual barrier problems, so the optimality conditions for those two problems are these conditions. So there is one small thing that I want to mention here because this is interesting and is very nice. So recall that if we have this function, let me call it f. Let me call f of t to highlight that this is a function of one variable. F of t, the function minus log of t. If we have f of t minus log of t, the derivative is minus 1 over t, right? Now, there is something that is really, I find this to be very pretty, and is, so for the logarithmic barrier function, we have that the gradient is, so first of all, what should the gradient be? The gradient of a function is a vector, right? Now here, the input, the vectors that we are talking about are matrices, right? So the gradient should be another matrix. Now this is what is incredibly pretty. The gradient of the logarithmic barrier is, you could guess what it is from here, is minus x inverse. Okay? So it's kind of like pretty math. So if you use this, then from there it follows that the KKT conditions for both the primal and dual problems, okay, the KKT conditions can be written like this. Okay, and why does that hold? Because in the KKT conditions, for example, in the primal, you have to take the gradient of the objective. So x inverse is going to come up. And that's what leads to the last, and in the dual, it would be S inverse, and that's what leads to the last equation there. Okay? So you can imagine now how the same machinery that we discussed on Monday would apply here. It's the same idea. Now, so this is the central path, the set of solutions to those equations as tau goes to 0 for tau positive. And the idea would be to chase points that are on the central path as tau goes to 0. So it's almost identical to what we did for linear programming. So we want to chase points that are on the central path. And I guess technically there is a little typo there, right? On the right-hand side, I should have put big X and big S, right? Because they're matrices, big X and big S. So I just noticed that this moment. And then the two issues that we need to worry about are the same ones that we had to worry about last time. We need to define some kind of proximity to the central path, and we want to define how we update the iterates. Okay? So the notation, we are going to essentially just extend the notation from before. F0 is essentially the same thing that we had before, the set of primal and dual strictly feasible points. And then mu is associated to the gap between a pair of primal and dual problems. So mu of xs, just as before, is x dot s divided by n. And now, in the linear programming case, we needed to measure how close the vector xi, si was the vector of all ones with mu in all multiplied by mu. So here, again, this df, so this so-called df, this is some kind of measure of proximity of xs to mu I. So we somehow want to, if we insisted on x as being equal to mu I, right? That would be like the extreme when the neighborhood that we're taking is exactly the central path. So if we leave a little bit of wiggle room there, we get a neighborhood of the central path. So that's what this D defines. We don't require that XS be exactly equal to the to mu times the identity. Instead, we measure some kind of distance between XS and mu times the identity. So there is a bit more deep mathematics that goes behind this. The distance, this is the Frobenius distance. We can think about the distance as looking at how far the eigenvalues of xs are from the vector that has mu in all the components. Or equivalently, the Frobenius norm between those two matrices, x inverse s, x1 half s, x1 half, and mu times the identity. But the important thing about that is D is a measure of how these two things are apart. And then, given some theta between 0 and 1, we define the local neighborhood here very much in the same spirit as the local neighborhood for the linear programming case. Okay? All right. Now, remember, the Newton step is kind of the crux of the algorithm. So the Newton step, we remember the central path equations are the equations that are there at the top. So the Newton step would be a linearization of those equations. Okay? A linearization of those equations. So let me skip one slide here for a moment and tell you how things would work out if you do the proper thing. So this algorithm is essentially identical to the algorithm, the short step path following method for linear programming, in the sense that the drill is exactly the same. We take two constants. One of them defines how close we stay to the central path. The other one defines how fast we decrease tau. And then at each step, well, we start with an initial point that is in the neighborhood of the central path. And at each point, we update. And we update with something that is like a Newton step. Okay? It's a Newton step. However, there is some nuances that occur in semi-definite programming. And we do something that is like a Newton step, but it's called the nested of thought direction. So, but bear with me for a moment. The key step here is that it's very similar to a Newton step. I'll detail this after the break. And then we update, and then we have, again, the same properties. So this is almost identical to what we did last time for linear programming. So we have that the algorithm here gets us iterates that are in that local neighborhood, and the mu of the iterates decreases linearly to 0. So because it decreases linearly to 0, then as a corollary, it follows that if we want primal and dual problems with a duality gap epsilon, we need to perform roughly log 1 over epsilon steps modulo some constants. Okay? And then we also have some long step and infeasible algorithms, very much as we did for linear programming. Okay? So there is one subtle point that I want to spend a little bit of time discussing, and is the Newton step, because there is some nuances about the Newton step. Now, since this is a little bit loaded, maybe this is a good moment for our usual short break. So let's take about 4 minutes stretch, and then I'll tell you about the Newton step. This is kind of the key technical component. So let's take a little break. I'll get a sip of water. Well, did we lose anyone? Okay, maybe I'll mention something that is not about the Newton step, but something that a student asked me, and I think this is this is a good point to maybe discuss a little bit more. So someone was asking me during the break, well, the Slater condition, do we actually need it for both the primal and dual problems? Okay, and so this kind of hones in on kind of some subtleties about what exactly do we need for a strong duality to hold. So let me say a bit more about this. If you have one of the two problems, let's say the primal problem, okay, only one of them satisfy this later condition, okay, if that happens, then strong duality will hold. And also the dual problem attains the optimal value. All right, so to ensure strong duality, to ensure that the optimal values match, it would suffice to have Slater condition only for one of them. But to ensure that they both are attained, one way of ensuring that is to assume the Slater condition for both. Okay. When you assume Slater condition, that only implies attainment for the dual problem, but not for the primal problem. So that's why this is the more kind of practical way of stating a nice set of probably stronger than necessary conditions for strong duality, but some that are very frequently satisfied and that are easy to work with and easy to remember also. All right, so let me spend a little bit of time on the subtle point here of the Newton step, okay? And the Newton step leads to something called the Nesterov-Tott directions. So the Newton step, once again, the name of the game is we want to solve that system of equations, okay? So typically, for a feasible method, so a feasible method would satisfy a y plus s minus c equal to 0, ax equal to, minus b equal to 0, and then xs not equal to tau I. Okay, so a feasible method typically would maintain the first two, but not this one. Okay, this is the difficult one that we would need to work towards. So, and this is exactly the same, a similar thing was what we had in linear programming. So, what would be natural to do, the natural kind of linearization, would be, think about this again as our g function, right? G of x, y, s. We want that to be, I guess, that minus 0, 0, tau I, or I guess, yeah, that. We want that to be equal to 0. So the most natural thing to do would be to look at this and linearize this. Look at the derivative of that, the Jacobian of that system of nonlinear equations. The Jacobian of the first two is completely straightforward because they're already linear. They're already linear, so that's completely straightforward. A star I, A, 0, 0. And if you think about the last equation, we have xs. The natural thing to do would be to say, okay, so I'm linearizing that. So the term that multiplies x is s, and the terms that multiply s is x. So we have s delta x plus x delta s, right? That would be the last one. So the natural linearization of xs minus tau I equal to 0 is x delta s plus s delta x, right? And this would be tau I minus xs. So this would be kind of the natural one. But there is a subtle point that occurs here. We run into issues of symmetry because this is one of the first things that you learn in linear algebra, right? If you take two matrices that are symmetric and you multiply them, the product is not necessarily symmetric, okay? So even though x and s may be symmetric, xs may not be symmetric. So if you just solve that Newton system kind of naively, delta x and delta s may not be symmetric matrices. So you kind of step out of your space. So you need to ensure that somehow you stay in the space of symmetric matrices. So to do that, one way of doing that is to revisit the idea of Newton's method. So again, the crux of Newton's method is if we want to solve a system of equations, we linearize, right? And then we solve that linearization of that system of equations. So if we want to linearize this, what I attempted to do here, if we want to linearize this, there is a way to linearize that maintains the symmetry. Let me show you one. If we rewrite the equation in terms by dividing by x, okay? So if we rewrite the equation as s minus tau x inverse, and now we linearize this, the linearization of s is delta s. The linearization of x inverse, this is a kind of a cool calculus exercise. I told you a little bit ago that the gradient of the logarithmic barrier is x inverse. The Hessian is that function. So let me write it down here. So this is kind of like a neat calculus fact. So for f of x equal to negative log determinant of x, the gradient is x inverse, and the Hessian is the following matrix. So the Hessian is a little tricky because the Hessian has to be, the Hessian this would be like a matrix that is n squared by n squared. So it's easier to think about what happens to the Hessian if I apply it to another vector. So if I apply the Hessian to, say, z, what do I get? So when I multiply the Hessian by a vector, I get a vector. So if I apply the Hessian of this to another matrix, what I get is x inverse z x inverse. Okay? So what happens here is when we linearize x inverse, then we get that potential linearization, the first one. If we instead rewrite the same equation as in the bottom, divide by s, then we get this other linearization. Okay? Now, these two linearizations are fine in the sense that they don't violate, they don't get me out of the space of symmetric matrices. They stay where they are supposed to stay. But we would like something that is primal dual, something that is in between these two. So that's what these guys, Nesterov and Todd, developed. Nesterov and Todd. So Nesterov was the same Nesterov that I mentioned earlier. And I think this happened one time that Nesterov was visiting Cornell for a semester, and then these two guys were really one of the most important, most prominent optimizers of the time, and they came up with this really brilliant idea. So the proper primal dual linearization would be some kind of average of the first one. The first one would be kind of a primal linearization. The first one is the same one that you would get if you applied the barrier method to the primal problem. The second one is what you would obtain if you apply the barrier method to the dual problem. And then the Nesterov-Todd direction is some kind of average of the two. So the Nesterov-Todd direction is something that you can rewrite. You replace X inverse with W inverse, or you replace in this equation here S inverse with W. And what is W? W is something that is like a geometric mean of X and S. W is that good-looking matrix there. So the nested of thought direction, is if we linearize the last equation that way. And what is very special about the nested of thought direction is that once you get through that, say, important technical step, then the short step method then extends nicely, and it has the same properties as the short step path following algorithm for linear programming. So this, I would say, is the second important conceptual difference between linear programming and semi-definite programming. The Newton step equations in semi-definite programming, they're more complicated. They are these so-called nested of thought directions. So in the last few minutes that I have, I don't have much time, so I just want to, in the last few minutes, again, I want to reiterate that we get the same kind of result as for linear programming. And again, this is of theoretical interest. And then, based on this, we can push this farther to long-step algorithms and to infeasible algorithms, very much in the same spirit as in linear programming. The numerical linear algebra gets a lot more involved because you're working with matrices. And sometimes you have to take square roots of matrices. So, it's not light. Numerically, it's much more involved. But conceptually, the algorithms extend. And then, what is really cool is that we can take this even farther. That is, to a class of cones called self-scaled cones. So I'll describe this really quickly. The idea is we can think about both linear and semi-definite programming as that kind of problem, where in the case of linear programming, the cone is Rn+. In the case of semi-definite programming, the cone is the cone of positive semi-definite matrices. So again, these two guys, Nesterov and Todd, thought about, okay, all that we have built for linear programming and semi-definite programming, can that be taken further to a wider class of cones, of conic programming problems? And the answer is yes, provided that you come up with a suitable, say, barrier function for that cone. So let me skip the technicalities about the barrier function and instead give you some kind of canonical examples. The punchline here is that the main classes of self-scaled cones, so self-scaled cones would be cones for which essentially all of this machinery extends. They include, obviously, the non-negative ortho, that's the one that we discussed last time. The semi-definite, the positive semi-definite cone, that's the one that we just discussed. But it also includes other cones like the second-order cone. And in the second-order cone, the corresponding barrier function for the second-order cone is that barrier function. So remember, the second-order cone was that ice cream cone. It's what you normally think about when you think about a cone. And then the barrier function for that cone is that guy there. Any Cartesian product of those cones is also a self-scaled cones. And a little remark here, kind of a segue, is that self-scaled cones is kind of a very neat mathematical fact. They coincide with a class of cones called symmetric cones that have been studied in other areas of mathematics. So it's a really neat kind of mathematical class of objects. And from the point of view of optimization, essentially what this says is that everything that we have discussed extends not only to semi-definite programming, but to products of semi-definite cones, second-order cones, and non-negative orthos. So the very last thing that I want to say is, maybe I can say, well, there is all the relevant machinery. We have primal problem, dual problem. Self-scaled cones are self-dual. And then we have optimality conditions. Then we have something like the central path. You have a Newton, a nested of thought direction, and then you have neighborhoods of the central path, and all of the previous machinery extends. So of course there are technicalities, but the main takeaway is that all of the machinery of interior point methods for linear and semi-definite programming extends to these self-scaled cones. Now, what I want to do in the last 2 minutes is tell you about a couple of conic programming solvers. So this is not just nice theory, but it's something that also people have implemented and used. It does take a substantial amount of effort to code things, especially for semi-definite programming. But luckily, there have been some diligent researchers who have done that. And to explain one of them, let me tell you about a certain kind of operation that we have in some way referred to a few times. So you can always think about this set of n by n matrices as a vector of length n squared. And in MATLAB, that's called the VEC mapping. Okay? VEC converts n by n matrices into vectors. And then MAT would be the inverse mapping. Okay? And then if you look at x dot s, that's the same as VEC x transpose VEC s. Now, Sedumi was developed by a Dutch mathematician, Jos Sturm, who sadly passed away about 10 years ago. He was really a brilliant optimizer. He developed Sedumi, and it has this really neat syntax. You can use it in MATLAB. What you do is just type Sedumi A, B, C, K, where A, B, C, and K define these two primal and dual conic problems. Now, K could be any combination of free variables, non-negative variables, semi-definite variables, and second-order cones. So you define K that way. So let me just give you one example. This probably is the best way to illustrate this. So the example that I want to show you is something called the theta function. So let me recall what the theta function is, and I'll leave you with this. So recall the theta function. So this is Lovász theta function. So given a graph with some vertices and some edges, the theta function of G, this is the max of 1, 1, x. So we add all the components of x, subject to identity times x is equal to 1, and x ij equal to 0 for ij an edge of the graph, and x a positive semi-definite. And the theta function is something that people who do combinatorial optimization are very fond of because it has all sorts of neat properties. It's sandwiched between the clique number and the chromatic number of the complement of G. So this is a little code that, given a graph G, defines A, B, C, and K, so that you can compute this, you can solve this semi-definite program. So for example, this, oh, I thought I had done this. There. So G, if G is that graph, so those are the edges of G, then when I do this, this constructs the instance, the semi-definite programming instance. So it builds C, A, and B. Okay? And now, if I want to solve this, then I get, if I look at mat x, that is the solution to this semi-definite program. Okay? If you, just for reality check, if you look at the eigenvalues of mat of x, that's, they're all positive because they have to be, right? It's a positive semi-definite problem. If you can play around with this if you are interested in solving any kind of small semi-definite program. Sedumi works very well. You could play around, for example, with the nuclear norm minimization for small problems. For big problems, we run into difficulties because for big problems, there is a major bottleneck in semi-definite programming, in interior point methods for semi-definite programming. Can anyone guess what is the major, say, bottleneck, the computational major overhead that you need to pay when you solve a semi-definite program with interior point methods? Any idea where you could run into that? Yes. Well, computing the Hessian, but most important, solving the Newton, I guess the nested of thought directions. Okay, the nested of thought directions are very involved. Essentially, you need to solve something like this, where this Hessian, the Hessian here, is a very complicated Hessian. For a semi-definite program, it's a Hessian of a matrix. Okay, so if the matrix is 100 by 100, you are working with many variables, right? And that could be computationally challenging. All right, so with that, I'll conclude. Maybe some references. If you want to learn more about semi-definite interior point methods, these are some of the nicest references for that topic. In particular, the last two papers describe more of the details of what it goes into the implementation of interior point methods for semi-definite programming. And with that, I'll stop. Ryan will be back next week. I'm sure you will be pleased to see him, and he will be pleased to see you. And I thank you very much for your attention. I'll stop here.